Welcome to this explainer, brought to you by Forge College. I am so excited to guide you through today's topic, building automated deployment tasks. In our previous lesson, we covered the core design principles of creating reliable deployment scripts for Solana. Today, we're taking those discrete, reliable steps and weaving them into a highly intelligent, fully automated sequence. Think about it this way. Running manual deployments is a lot like trying to build a complex sports car completely blindfolded. You're just kind of feeling around in the dark, desperately hoping you don't miss a step. But what we're building today is a precision assembly line. We're going to engineer a smart, autonomous deployment robot that takes all the guesswork out of pushing your applications to the Solana mainnet. Here is our blueprint for today. We're covering why automate, the magic of idempotency, the detect, decide, apply, verify loop, keeping secrets safe, AI scaffolding, and finally, the pipeline.
Section 1. Why automate? It all comes down to dramatically reducing human error.
We absolutely have to build a state machine. Manual deployments, they're tedious, they're stressful, and honestly, they're highly error-prone. Automated deployments, on the other hand, are repeatable, sequence-driven, and completely auditable. We want a smooth process where the output of one step feeds perfectly into the input of the next. No more sitting there manually mashing buttons on a keyboard and praying it all works out. Section 2. The magic of idempotency. This is all about hitting the exact same state every single time.
Now, effectful idempotency might sound like a massive computer science buzzword, but it's actually a pretty simple, brilliant concept. It just means our deployment robot is smart enough to check its surroundings before doing its job. Think of a robotic arm on our car assembly line. If a tire's already bolted on, it's not going to try to jam a second tire onto the exact same axle, right? For us, an idempotent step creates the exact same end state on the Solana blockchain whether you run the script once, twice, or 100 times. It only applies changes when changes are actually needed.
But that brings up a really crucial question. How does our script actually know what's already on the blockchain before it acts? How does it peek at the current state of a Solana program account to figure out if our binary is already sitting there?
That takes us to Section 3, Detect, Decide, Apply, Verify. Welcome to the DDA loop. This loop is literally the heartbeat of our automation. First up, detect. We read the current environment without touching a single thing. Second, decide. We run a simple true or false check. Do we actually need to do work here? Third, apply. If the answer is yes, we do the heavy lifting. And finally, verify. We immediately double-check that our change actually took effect.
Think of this as your ultimate engineering blueprint. It perfectly maps out how to tie deployment steps to detection and verification strategies. For example, before uploading, your script computes a local SHA-256 checksum of your compiled artifact. Then, it queries the on-chain data hash and compares the two. If they match, boom, it skips the upload entirely. No wasting resources or blindly deploying the same exact program twice. Or, if you initialize an account, you query its existence and check its owner first. It's always the same rhythm. Detect, decide, apply, verify.
Section 4. Keep your secrets safe. Let's lock down those credentials.
Look, hardcoding your RPC endpoints, or worse, your private key paths directly into your scripts, is exactly like leaving the keys dangling in the ignition of a sports car. Anyone who looks at the code can just hop in and take it for a joyride. You absolutely must externalize your secrets. Read them from environment variables or dedicated secret vaults. This guarantees your automated script can safely run anywhere, whether that's in a cloud-based CI pipeline or locally on a teammate's laptop, without ever compromising your secure credentials.
Section 5. AI-assisted script scaffolding. Let's talk about vibe coding your foundation. We can actually bring in a super fast AI assistant to scaffold our assembly line in seconds. The trick is giving it a highly specific, well-engineered prompt. We ask it to generate a POSIX-compatible shell script that computes a SHA-256 hash. We ask it to include a little Node.js helper to fetch that crucial on-chain data hash for comparison. And we strictly instruct it to pull all secrets from environment variables. AI is fantastic at writing this boilerplate, handing you a rock-solid foundation that you can then review and refine. And when you scaffold that script, make absolutely sure it includes different operating modes, especially a dry run mode. A dry run is basically your full dress rehearsal. It runs the detect and decide phases and prints out exactly what would happen without actually executing any changes or spending a single token on transaction fees. This is an absolute game changer for safe manual reviews and for testing your logic in CI pipelines before you pull the trigger on mainnet.
Finally, Section 6, the pipeline. Let's look at machine-readable logs. Remember, your script isn't just talking to you, it needs to communicate with other machines. By spitting out deterministic, JSON-like logs, your script creates a highly reliable contract. Continuous integration and monitoring systems can easily parse outputs like upload needed equals false or verify success equals true. And if verification fails, the script just exits with a clear error code, instantly telling your automated systems to halt the pipeline. Everything stays perfectly in sync.
So let's quickly recap the whole shebang. Separate your decision logic from your actions using that detect, decide, apply, and verify loop. Enforce idempotency by checking local artifact checksums against on-chain program hashes. Keep those private keys miles away from your source code by externalizing your secrets, and always support dry runs for safe automated testing. Our blueprint is drawn and the assembly line is officially powered on. But I want to leave you with a thought. As we hand more and more power over to these autonomous DDAV loops, at what point does the deployment script actually become smarter than the developer who wrote it? It's pretty wild to think about. Thanks so much for joining me on this explainer. Be sure to visit forge.college to master even more Web3 engineering concepts. Catch you next time.